To prove the power rule, we first need to understand the binomial theorem, which is this equation right here. Keep in mind that n here is the number of terms, and we'll get to k later. This looks really scary at first, but let's decipher it bit by bit. Let's consider the binomial a plus b. If the binomial had an exponent of 1 like this, the answer is still a plus b, obviously. If the binomial had an exponent of 2, well, this just means that we're multiplying this binomial by itself, so a plus b multiplied by a plus b is just a squared of 2 plus 2ab plus b squared of 2. Similarly, if the binomial had an exponent of 3, we multiply itself 3 times. So the answer is a squared of 3 plus 3a squared of 2b plus 3ab squared plus b squared of 3. By now we can see a pattern. Notice that the exponents on the letter a goes down by 1 on each term. The first one is 3, then 2, then 1, then 0. Because there's an invisible 1 here. And anything with an exponent of 0 becomes 1, a descending pattern. The exponent on the letter b, on the other hand, goes up by 1 on each term. The first one is 0, then 1, then 2, then 3. To organize this pattern we see into a proper equation, we first need to assign a number to each term. Let's say a general term is represented by k. The first term is k equals 0. The second term is k equals 1. And the third term is k equals 2, and so on. Now we have the proper amount of letters to compile this pattern to an equation, which is this one right here. Keep in mind this is the equation for each term. If the exponent is 1, we will only have one of these things. If the exponent is 2, we will have 2 of these things added together, and so on. Let's do an example with this formula to see if it's correct. If we use a plus b squared of 3, we can see that in the first term, a's exponent will be 3 minus 0, so 3. Keep in mind that n is just a number of terms, and k equals 1 because this is the first term. B's exponent will be 0, so b is just 1. So we can ignore b here. The second term, a's exponent will be 3 minus 1, so 2. B's exponent will be 1. The third term, a's exponent will be 3 minus 2, so 1. B's exponent will be 2. The fourth term, a's exponent will be 3 minus 3, so 0. So we don't have to write a here. And b's exponent is 3. If we string all that together, we see that the exponents on the a and b's correspond with what we had earlier. Now we have taken care of the exponents. But you may have realized that we haven't touched on the coefficients yet. Well, the coefficients are a lot simpler. They're just numbers from the Pascal's triangle. The first row is for an exponent of 0, the second for 1, the third for 2, and we see that the numbers on the fourth row exactly correspond with the coefficient we got for our exponent of 3. Each of these coefficients on the Pascal's triangle can be summed up as n choose k, which can be written a bunch of ways. For example, if we want to find the coefficient on the second term of our exponent of 3, we know from here that it's supposed to be 3. We can check on the Pascal's triangle and see that it indeed shows 3. And we can do n choose k or 3 choose 1 and get 3. To sum all these terms all up like we did for the exponents earlier, we use the sigma notation. The equation would be like this. This part is the equation we established earlier. And the sigma tells us that we're doing this from k equals 0, the first term, to n, our final term. Putting all this together gives us an equation of this. So if we use the exponent of 3 and redo this all again, the first term, 3 choose 0, coefficient is 1, multiplied by this, which we've established earlier that a has the exponent of 3 and b has 0, plus the second term, k equals 1, 3 choose 1, coefficient is 3, a has the exponent of 2 and b has 1. The third term, k equals 2, 3 choose 2, coefficient is 3, a has the exponent of 1 and b has 2. The fourth term, k equals 3, 3 choose 3, coefficient is 1, a has the exponent of 0 and b has 3. And we have reached the ending number on here, so we stop. And we can see that we got the exact same answer as when we multiply itself 3 times. Now, with smaller exponents, it is more efficient to just multiply this a couple of times. But with large numbers, it becomes way too tedious. So this is actually a good method to work out each term instantaneously without having to expand, then add together all the same exponent terms, and so on. I'll explain in the next video how this plays into the proof of the power rule.